intersection of a little bit of kind of chemistry with weather. One of the things about these gas particles is that they have a lot of motion. We're going to actually call it motion kinetic energy. All these gas particles, most of them are nitrogen, some of them are oxygen, so 820. We have some kind of other gases. But it creates a pressure, which we're grateful for. So it's the motion of the gas particle that creates a pressure. So, for instance, when you go to inflate your tires, okay, I can never remember how much. Did your pen stop working?
No, it's like.
Oh, it blew up. Do you want to borrow it?
No, it's okay.
She's looking at it like. When you go to inflate your tires on your car, is it like 35 psi? I can
It tells
remember.
you on your tire.
Okay, it tells you on the tire, so I always have to look.
Read your tire.
So PSI stands for pounds per square inch. So in other words, 35, 65, I don't know, it makes a difference, of your tires, that means that those gases are kicking at 35 pounds per square inch of the tire that's contained in it. Okay, 35 psi. As we're working around the room, we're about 14 psi, 14 pounds per square inch. So those nitrogen and oxygen particles are kicking at us about 14. There's this kind of cool thing with astrobiology where you think, well, if we didn't have 14 psi on us as we evolved into the humans that we are, what would we look like? So, for instance, if we had, instead of 14 psi, if we had like 100 psi, we'd be like squatty little creatures. Astrobiology. So anyway, we have this pressure thing going on, and so this picture with the little circle, we kind of looked at this before, that's a parcel of air. If you look closely, you can see the two colors, the green, let's see, how does this work? I think the green are the oxygen and the red are the nitrogen. And you see the cute little Mickey Mouses, those are the water particles, water vapor particles that we measured last week in lab. So all gas particles create a bang, create a pressure. So like I said, a common unit for gas pressure is pounds per square inch, but actually when we talk about meteorology, when we talk about the pressure of the atmosphere, pounds per square inch isn't going to do it for us. Those units, for whatever reason, we don't go 14 psi, we actually go into different units for kind of what the pressure of the atmosphere usually is. And one of the cool things, and this is neat about particles, these are all 3 different gas particles, nitrogen, oxygen, and water vapor, okay, all little cute little gas particles, and they all gang up together to make a collective bang. So if, for instance, you have nitrogen at 10, oxygen at 3, and water at 1 psi, collectively they're looking about 14 psi. I think that's kind of cool. So instead of pounds per square inch, we're talking about kind of the pressure of the atmosphere. And we're going to see, if you're a weather junkie, you know that atmospheric pressure is one of those things that actually folks track to, it's called tendency. It's basically, is the pressure rising or falling? Okay. As to what's the forecast for the weather. So instead of pounds per square inch, you might hear them say inches. Now they won't say inches of mercury, but that's what it is. You'll basically see just inches. What's the pressure? Oh, it's 29 inches, 29.8 inches. But they mean of mercury. And of course, mercury over here on the periodic table, the symbol for mercury is this blue guy right here. Blue means he's a liquid under normal atmospheric pressures and temperatures, so Hg. So I'm going to show you why they call it inches of mercury coming up. So this actually is one way to measure atmospheric pressure. And this is where the mercury comes in. Mercury's silver. It used to be, and when I was a kid growing up, if your thermometer broke, you're like, awesome, because this silvery stuff would come out of your thermometer and you'd be like playing around with it because liquid mercury's kind of cool. But now we know that's not a good idea. There's something called Mad Hatter's disease, and it came from folks who mine mercury, and it makes you go crazy. I'm fine. But anyway, so now thermometers don't have, yeah, that's debatable. Now thermometers don't have liquid mercury, they have liquid alcohol. Okay, so it's just better. But anyway, a mercury barometer, just since the liquid mercury is so heavy, it works real well. What happens is this is actually glass tube, and what they did was this glass tube is closed up here and it's open down here. Okay, this is an open pan of mercury. And so in order to get this ready, what they did is they pulled a vacuum. They pulled a vacuum in this tube closed at one end, and then they put their finger over it. They didn't really. Then they put it in here, and then they just let the kind of level settle. Now the level in here that's up the tube will settle according to what pressure is on the pan. It's kind of cool. So you figure those two red arrows are the pressure of the atmosphere. And so as the pressure of the atmosphere increases, more will go up the tube. So when they're talking about inches of mercury, they're saying when inches increase, there's more pressure. When inches decrease, there's less pressure. So instead of inches of mercury, okay, actually when we do physical science, a lot of times, if we're going to use mercury, it won't be inches, it'll be millimeters, mm's. But in weather, a lot of times we use millibars, MBs. Milli means, or M means milli, and B in this case means bars. So cute little millibars. So here we're running about 14 psi, pounds per square inch, with the nitrogen, oxygen, and gas particles mostly. And that's about 1,007 millibars. It's also about 760 millimeters of mercury, about 30 inches of mercury. Okay, yeah, millibars or MBs. Okay, so that's atmospheric pressure. I'm going to show you why that's so important. Try to convince you why that's so important. So here's the deal about pressure, and it's kind of like if you follow athletes, or if you just climbed a mountain yourself, you know that the air gets thinner. And so that's actually in context of what I need to talk about here. The air gets thinner as you go up a mountain, and this figure kind of shows you as you go up in elevation, that's along the y-axis. Along the x-axis we have pressure. So this red line is showing you the pressure at different elevations. Excuse me. So at like 4 kilometers above the Earth's surface, you're running about 600 millibars. Okay, I told you we're about 1,000 millibars here. Okay, 1,000 millibars at the Earth's surface. Okay, as you climb Mount Everest, now instead of 1,000, you're at, what is that, about 300 millibars of pressure, which is a fraction of 1,000, okay? You keep going up and then it's less and less particles. The Red Bull video that we watched the other day, remember when he got up at upper elevations, the skies were no longer blue, because what makes the skies blue is the presence of oxygen and nitrogen, so they're more wrongly scattering. So this is kind of a nice little box. Okay, this box is showing you kind of the same thing. These are gas particles, and you can see the density of the gas particles at lower elevations is greater. At upper elevations, the density of gas particles is less. So as you climb a mountain, you're going to have still the kind of 80-20 mixture of nitrogen and oxygen. As you climb a mountain, you just have less air in general, less gas particles. There's less bang against you. Okay, and you have less oxygen to suck in. So I've heard that athletes, what they have to do is it's like if they're playing in Colorado, you might want to go there and kind of equilibrate your body to that amount of oxygen. Okay, so thinner is the word there. So the air gets thinner, less pressure. We're going to be talking about differences in pressure, because differences in pressure, I'll go ahead and tell you what the topic of the next part is. Differences in pressure is what gives us wind. And wind is a player in our weather. One of the things we want to know about today is what's the temperature, and that's kind of an air mass thing a little bit. Where did that air come from? Did it come from the tropics, or did it come from Canada? That's kind of, we'll know what the temperature is going to be like. The other thing we want to know about is wind. So we've already run into the H's and the L's on our weather map. I'm going to go ahead and put them here. So here we go. Here's my H, and here's my L. H's mean high pressure, L means low pressure. So if I look at a column above me, I have what's called, and the word gradient means change. I have a pressure gradient, a pressure change. I've got high pressure here, low pressure here, everywhere. All right. I actually printed these out so you wouldn't get hand cramp. Sometimes you're like, oh my gosh, that's crazy. So these are, this is this slide. Or whatever. So these will be due when we meet again Friday.
We don't have school Friday.
Thank you. We don't have school Friday. Good job, Melissa. I've got to be somewhere, but y'all don't have to be here.
So Monday?
Do Monday, yes. Me. Alrighty. On to part 4. This works. I have to check on this stat. So that's, there's nothing to do there. I got this completed. Okay. So we'll see if we get through with this. And actually, if we get through this with this, I might even start with the next part. Because this is kind of short. So here we go. I brought along some props for this one, hopefully. So pressure. What's different about the last slide and this slide is now I'm talking about surface pressures. So as I've drawn this map up here to talk about thunder snow, when I'm talking about surface pressures, I'm not talking about this pressure gradient between, like if you're standing here, we have a high down here and we have a low up there. You know that one exists. Now I need to talk about this difference here, where we might have a high here and a low here. This is what we call, let's see, this one right here, I get my vertical and horizontals mixed up, but this is what we call vertical pressure gradient, and this is what we call horizontal pressure, P for pressure gradient. All right. So horizontal differences in pressures. 2 chunks of air sitting side by side at the same elevation can be different. So I've drawn H's and L's here. Actually, these H's and L's, these would be when we look at a map, when we look at a weather map, these would be the H's and L's you see on the weather map. So I need to talk about why you would get those differences. And then we'll talk about how those differences create wind. So why would you get the differences? There's 3 main reasons where you can get the differences. One is temperature. So if we look at these here kind of, and I have to be careful because, you know, not all see the same colors, but the left one's blue, it's colder, and the right one's red, it's warmer. So if I look down here at the surface, hopefully you can see that we have a density difference. This is actually more dense with the cold, and this is less dense with the hot. So here I'm going to go ahead on this slide and put an H where it's cold. It means a high pressure. I put an L where it's warm. One of the things I might have, that L doesn't show very good, does it? But it's an L there. One of the things I mentioned is that just in general, just general trends about what the weather's going to be like. It's all sorts of like general trends. One is if you have a big temperature swing, you can expect during that temperature swing or shortly after that temperature swing, you're going to get some kind of crazy winds. And this is why, because you had cold temperatures that have a high pressure, and you have warm temperatures that bring a low pressure. All right. What else do we have? Moisture. So the other day, you guys measured the humidity. Now remember, there's different ways to talk about humidity. There's relative humidity. That means how close you are to being saturated. There's absolute humidity, kind of how many gas particles there are in the air. So that's kind of 2 different ways. So more like absolute humidity. If your air is humid, sometimes it's kind of counterintuitive, which means it seems backwards. If the air is humid, if you feel so oppressed, you're like, I know it's going to be a high pressure, but it's just the opposite. If the air is humid, that means actually it's a low pressure, relatively speaking. And that has to do with how much a water molecule weighs and how much a nitrogen molecule weighs. So if it's relatively humid, okay, a moist air, you're actually going to be a low pressure. Dry air, you're going to be a high pressure. And actually, this goes back to when we talked about air masses. We said we have, generally speaking, air masses can be different temperatures. Generally speaking, air masses can be different moisture contents. So if a chunk of air dwelled over an ocean and then got on the move, okay, it's going to be moist, maritime. If a chunk of air dwelled over land, it's going to pick up the characteristics to be dry. So this is another way you can get those surface pressure differences. The last one is this one. This one is maybe one of my favorite ones. This is, do you remember Florida, when we talked about ways of having a chunk of air lift up? And we looked at the peninsula of Florida, and we said a chunk of air could lift up, and this is supposed to be Florida. This is the United States. I am terrible drawing in the United States. Hopefully, it kind of looks like the United States to me. Looks like a cow's udder right now. But we said you could, the way the winds work sometimes, we have wind kind of coming up, pushing air onto land. And we said that actually as it's slick over the ocean, it's nice and fast, and it's hit the land. It's like, oh my gosh, it kind of builds up, piles up. The other thing is that actually these two chunks of air are converging. And so that actually is a good lifting mechanism. And I liken it to if you're on the playground with a bunch of 6-year-olds and you have a bag of candy. I mean, a bunch of 6-year-olds. Let's make them hungry, like right before lunch. And you have a bag of candy or a pinata or whatever, and you say, "Come and get it," and all the kids, okay, that's converging. Okay, so what did the density happen right there? It increased. Okay, so when air converges, you get a high. And then actually, I can take that same analogy and say, so man, they just stayed there and I mean, you had a pile of candy, like they could swim in the candy. They're like, and then someone gets sick. Okay, so someone gets blah. So they like throw up, and then you actually have not converging, but diverging. So then actually diverging phenomenon brings you low pressures. So anyway, that's true. So converging, that would be the candy. That creates your automatic high pressure. Diverging air will create a low. And these are all important players if you kind of go on to, or I'll kind of convince you a few of these. Let's see, what word are we there? Converging, oh sorry, word was converging there. So the convergence means to come together, you create a high pressure. Diverge means to split apart, you create a low pressure. Makes sense to me. I like things that make sense to me. All right, so I mentioned that pressure, atmospheric pressure, is a player in what sort of weather we can expect. At our house, we've got, and they don't cost that much anymore. We've got one of those little weather monitoring stations, so we put the sensor outdoors under our porch, which I'm not sure if that's, but it works okay. And then inside we have what it's measuring. And then the thing, our inside will tell us the current temperature in and out, and tell us the relative humidity in and out, which is kind of cool. And then it will tell us the pressure outside. And based upon that pressure, it will go ahead and it will estimate what sort of weather we can expect. So here we go. Anytime you see barometric pressure, think atmospheric pressure. It means the same thing. Barometric pressure and atmospheric pressure mean the same thing. So atmospheric pressure, barometric pressure rising, you should expect clear skies. So this is an old-timey, actually, barometer. And a barometer is a thing, I showed you how to measure atmospheric pressure using that liquid mercury. That's dangerous. So this is a better device, a more mobile device. Actually, I've got a few of these lying around. I forgot to bring one. A barometer to measure the pressure. And what this is saying, what a barometer does is you can, let's see, I think the black one is what you can move here, and the gold one is actually what the device moves. So what you do is you set the black one on what it is, and you let it go. So this is actually saying that compared to what it was, our pressure is rising, our tendency is rising. So that's how these kind of things work. So rising pressure, clear skies. Falling pressure, clouds or precip. So you have three options: rising, falling, or steady. And actually those arrows, I know they're kind of cheesy, rising, falling, steady, a sideways arrow. Those are actually shorthand notation, what meteorologists will use. So falling pressure, so in this case, what a falling pressure sort of deal would have been, where I mark the black one, that's the one that's movable by me. A few hours later, I come back and my gold one, which moves with the device, is to the left of it. That means it's falling, and you can actually see here on the barometer, it's printed stormy, rainy, okay, fair, or very dry. So that's kind of how, we call that pressure tendency. Rising, tendency falling, tendency steady. So, all right, here is a weather map. Okay. I'm a little disappointed in the weather maps online these days. They don't, I guess I'm just getting too old to what I'm used to. But the weather maps, I couldn't find a good one to show you these black lines. Let's see if I can kind of make this bigger. If I click this, nope. There it goes. Okay. There we go. So this is, I think, kind of important. You see two bullseyes. So it's like an eye test. You see two bullseyes. Okay. We're going to talk a little bit more about those bullseyes. But in the center of those bullseyes, we have an L and we have an H. Of course, L is low and H is high. We've talked about that. The thing that's creating those bullseyes is kind of similar to, I liken it to, if you've done much with how tall is a mountain? You know, we actually have these, they're called isoplugs, but on how tall is a mountain, I can erase my, we would take the tippy top of the mountain, and that would be the middle of our circle. How tall is a mountain? I'm switching gears. I'm trying to kind of connect it here. These are what we call contour maps. So this would be the tippy top of my mountain, and then as I step down, that might be 10 feet lower. This would be 10 feet lower. This is a contour map of elevation. This would be 10 feet lower, 10 feet lower. So this would be tall or high elevation. This would be the low elevation. Okay? People are kind of used to that. It's called a contour map. Well, these are contour maps, but they're contour maps of pressure. So if we start with let's start with the H. That'd be like the tippy top of a mountain. So notice that, 1036. That actually means, yeah, that's right. That means in terms of millibars, MBs, you're running all of those locations around that circle, 1,036 millibars. We're going to step down. Notice the one outside. It differs, it's 4 lower, right? Stepping in, 1,032. What's the next one? 4 lower, 1028. What's the next one? 4 lower, 1024, 1020. So these are very similar to contour maps, like elevation contour maps that we're used to. So, very good. Central high, okay, central high. Well, let's look at the central low. Central low is not like, central low must be, then I'm going to be stepping up, and we are. Check this out. This middle contour line, 996 millibars. The next one, up 4, 1,000 millibars. The next one, up 4, 1,004 millibars. The next, up 4, 1,008 millibars. Okay, so like that. So we have a central high and a central low pressure. And I think we'll get to this, but oftentimes, kind of going across the United States, you'll kind of see this alternating high, low, high, low. And they bring weather with them. It's not quite this simple, but highs generally bring like clear skies, lows bring clouds and precip. And so actually this gets back to what we've been seeing for the last 4, 5, 6 weeks. If it is cyclical, kind of like I'm going to go high, low, high, low, high, low. And if those cycles are about 7 days, you're screwed. So we just kind of keep, it's like Groundhog Day. Okay? depending upon that. To me, I think that's kind of what we'll do. Now, the other thing this map adds is these little lines with the flags. The more flags, the stronger the wind. So I'm going to talk about wind here and pressure coming up. But the no bars, are just no bars, yeah. The wind is very calm. The more flags, the stronger the wind. So if I was just going to glance at this, hopefully you guys would probably say the same. If I'm comparing the highs to the lows is windier. Lows is what's going to bring our more severe weather and such. So, let's see, what else do we got? So the word is pressure there. Now we're used to kind of the contour maps showing us elevation, but here the contour maps are showing us pressure. And these are called, specifically this contour map is called an isobar, isobaric. I think that comes from, remember the units are millibars, so isobaric, bars, baric. All right, so it looks like a bullseye. And the word is closer. So I said that the lows, if you kind of use this as your guide to what sort of wind conditions we got, it's definitely windier over here, and it's low. And the way this works is the closer these are, these lines, these circles, then actually the stronger the wind is going to be. And I'll try to kind of convince you of that. If I was going to draw, I'll go back to elevation. That's one sort of thing. And I'm going to draw another mountain situation where, again, the center is tall. Here's my peak. Okay. And then I'm going to step down, 5 meters here. And I'm going to step down 5 meters here. Okay. And then I'm going to step down, I'm going to actually run out of room, 5 meters here. Okay, to me, when I look up, if I call this A and this B, when I'm talking about B, man, it's a pretty gentle slope, isn't it? Yeah, and that's kind of what we got when we have what we call tight isobars, okay, versus not so tight isobars. And that's characteristic of a low and a high pressure too. All right, so here we go. Wind. Wind will always go from a high to a low. Just trying to think how I want to create wind. So an easy way to create wind, something that will move. I didn't think through this. Make a little ball here. Get a little bit of aerodynamics going on here. Okay. So if I go like this, if I fan it, I create wind. If I do that in slow motion, what I'm doing is I'm scooping up, this is so cool, guys. So these little cute little gas particles, I'm scooping them, I'm concentrating these gas particles. I'm making a high pressure here, okay, making a high pressure here, and here's normal. So that's actually what causes those gas particles, dude, I'm a high pressure, I'm out of here. So I'm gonna go everywhere but here, and where that is in front. Okay, so if you go like this, you're creating a high pressure, high. Okay, so the gas particles go from high to low. That's just it. Totally it. So I have some other ones. I love Dollar General or Dollar Tree. They're different. They're way different. I know. It's like. So, yeah, I don't know. Buy American, all that, but it's hard to beat. So I'm basically confining those cute little gas particles. And so here's the deal. If I go ahead and prick this, right, what's going to happen to the gas particles? My balloon if I prick. They're going to fly out of the little hole. If I put my hand in the little hole, oops, sorry. Oh, I hope nobody comes. I'm like, oh no, we're fine. Yeah, if it would have been more subtle prick, they would have come out of the little hole. But here, actually, it just kind of, those cute little gas particles were confined, and they're like, dude, if I have a way out, I'm out. Gas particles are just like that. And that's why we have wind that's created from a high to low pressure. So here we have, it kind of looks like a football field, where we have our H here, specifically, this is our pressure, and we have our L over here, and this is our pressure. So, of course, these cute little particles, high density, they're going to want to go to low density. It's what we call that gradient. We said there's all sorts, there's a pressure gradient, there's a temperature gradient. In biology, there's a sugar gradient, sodium chloride gradient. Okay. So this grade we call pressure gradient, means differences in pressures. Check this out. So here, this is kind of going back to my stepping down. Here we've got 4 millibars difference, 4 millibars difference, 4 millibars. These are all 4 millibars, but over here, they're closer together, so they're steeper. So that dense air, high pressure, has even more. This is going to be a stronger wind. This is going to be a stronger wind. And actually, you know, if you want to, you can do the whole fanning thing. I mean, if I'm just kind of doing it gentle, or if I'm going like this, I create more of a wind. I create more of a difference in pressure. So it makes sense. I like things that make sense. So these are the isobars we've been talking about. They're marked on the edge there. So we go from, they look like they're going every 10 millibars. Okay, so you can kind of see the direction of the wind. Kind of, this would be a northerly wind. We're going to talk, we'll talk more about winds. Why? Because our winds are usually kind of from the westish. We're going to talk about that, what we call prevailing westerly wind. But no, sometimes I'll look at this flag and you're like, uh-oh, they're coming from the east. That can't be good. Or from the north, that's bringing down the cold air. So this is kind of showing you what I've been talking about. Okay, so like I said, the greater the difference, so the closer those isobars, the closer those lines are marking different pressures, then the steeper the pressure gradient force and the faster or stronger the wind. And then that kind of goes back to the previous map we looked at, where the lows, the central lows, are nice and tight. The highs are the highs aren't much like a bullseye, actually, kind of like, we saw it like a bullseye, but they're kind of blobby and they're far apart. All right, I have a video to show you. So there's 2 feels like temperatures. Let's see what this video does. We talked about the humidity one, and that's the effect, and the heat index. Both only apply to living things, specifically living things that I think are warm-blooded. So let's see, what did we have? These are in Celsius, trapped. Disappointed movie. I'll have to find a movie. Oh. I'm going back for more. This guy. All right. Come back. So we have to convert 34 Celsius. It should be a convert 34 and 27. Sorry. No, I did that the wrong way, didn't I? That's what you get for being in a hurry. Okay. Final answer. We've come this far. Okay. So 1.1 degrees Celsius. That's the actual thermometer temperature. Wait, yeah. And the feels like is 27. So this is thermometer, this is feels like. Oh, gosh. All right. So negative 2.7, 2.8 degrees Celsius. And the wind was 9. All right. Now with all of that in mind, that's not you guys. You guys are right. See, I told you it feels like a Monday. You guys are right here. Dun, dun, dun. Wonder if, yeah, miles per hour, so that's good. Oh, it's not going to be on there even. Yeah, it'd be between 9 and 10. All right. So slow. Okay, so now, feels like temperature chart, where we just need to see where our 9 miles per hour intersects with 30, or this intersects with 1.1 degrees Celsius, and I have lost my pen. We don't have 9, but we have 10. And we don't have, we have 35. Okay. It was like degrees Fahrenheit. Oh my goodness gracious. Why didn't anybody tell me that? Anyway, so do you see where this is how fast our wind's blowing, and this is actually the thermometer temperature, and this is the feels like temperature. Goodness gracious. So the way this works is, and I think it kind of lends itself to a picture. Here's my Homer J. Simpson arm, because he doesn't have 5 fingers. Now this is arm, and one of the things about us as warm-bodied animals is we ooze. This is my oozing thermal energy. And we count on keeping that little bit of thermal energy with us wherever we go. Well, it's pretty easy. If you kind of think of wind kind of blowing across your arm, it takes your blanket, and that's why we feel colder than it really is. Okay. So, here we go. I know this says recall, and we haven't covered Newton's laws of motion yet. But it's coming when we talk about physics. Newton has 3 laws of motion, and one of them is kind of obvious. And it's funny to think about people who didn't know this. Just a minute ago, I was like, I made this, and move, and like, okay, that can't just magically move. People used to think it could magically move. There must be some force making it move. Yeah. So Newton says that anything that moves must have a force, an outside force working on it. And this actually is kind of what we can see in the wind. So Newton said that we have this wind flowing at a certain speed. Aloft means upper elevations. So wind goes faster at upper elevations. I think I might have talked about this before. We do this in physics, where the length of the arrow is talking about how fast it is. So you can see here at the most upper elevations going real fast. Go closer to the Earth's surface, it slows down. Here, actually, we have it kind of tumbling. So there must be some force making it change its motion. And in this case, it's the force of friction, ultimately, in some cases, stopping the wind. If you're on another planet with no surface features, watch out. Really, really, really fast wind. So one of the things we're going to hit on next Monday, not Friday, is this idea of a chunk of air not going straight, but a chunk of air taking, like you see, this kind of curve. A chunk of air taking this curve. Now, it's almost kind of like an apparent curve rather than a real curve. A chunk of air that wants to go from point A to point B, this is the target, it won't. It actually, if it's left the Earth's surface and it's related to the fact that the Earth is spinning, it's going to end up appearing to deflect and end up missing its target and ending up over here, caused by the Earth spinning on its axis of rotation underneath it. And that's called the Coriolis effect, Coriolis force. So I think that's a good place to end it. And have a little video, I know, because I found it today, to show you.